Okay, long answer sections. So we need to define force vibrations. So these are force vibrations are vibrations in which a periodic driving force is applied to an oscillating system. Okay, we can go into it and we can say if the frequency is very low, then the oscillator is in phase with the driver. But resonance, of course, occurs when the frequency of the driving force is equal to the natural frequency of the system. It doesn't mean they're in phase though. At resonance, we have a maximum amplitude, and the phase difference between the driver and the oscillator is pi upon 2 radians. Okay, they're 90 degrees out of phase. Now, as the frequency of the driver gets larger than the natural frequency, the amplitude decreases and the phase difference approaches pi radians. So when it's very, very slow, remember, if you put in your driving force that way and you pull your string, the two will go very slowly like that. As the driving force goes fast, there's a phase difference of 90 degrees, and as it gets really fast, then the reason it gets towards being 0 amplitude is because the phase difference starts to approach pi radians. Right, B. I think this one, this to me is obvious, but clearly not to most of you guys. Basically, if you've got a paper pendulum that is dangling on a string and you displace it, if it's got some mass, it's going to rotate for longer because it's just got more momentum. I would have said that's my logic. But if you want to put it into words, it's going to oscillate more or for longer, okay, with the ring. Okay, it's going to have more heavy down. Yeah, so basically, it's kind of interesting, really. I think I understand the words a little bit dodgy here, really. Basically, the cone oscillates for longer and has less damping when there is a ring on it. Okay, and the reason for this is that basically the energy of the system is proportional to the mass of the pendulum. If you think about what a pendulum is doing, it's going from kinetic energy to gravitational energy, to kinetic energy to gravitational energy, swinging backwards and forwards, making this transfer. Now, every swing, of course, it's going to lose some energy due to friction with the air. And of course, that work done is force times by delta S. And so the friction is the same for each pass. Well, I mean, as it gets less, as the distance gets less, the work done gets less, but the friction's constant. So what we could say there is a more massive pendulum, although a more massive pendulum will lose energy on each swing, it will lose a smaller proportion of its total energy. So the more massive it is, the more energy it has. It's going to have nothing to do with how much friction there is on for each given swing, and therefore you'll lose a smaller percentage of the energy, therefore there'll be less damping. Coulomb's law, money for jam, guys. For these 2 mark questions are the ones you just can't afford to throw away. They're so easy. I could teach my dog to learn these definitions, and you should be able to do it too. So, 2 charges, the force between 2 charges directly proportional to the product of the charges, that's the first mark, and inversely proportional to the square of their separation. Okay, I've put on there as long as they're treated as point charges, and I should really just put the force between 2 point charges in there. Anyway, potential. Question 2b shows us electrical potential varying with the inverse of the separation. So, quite a tricky question this. You have to think about it for a bit. We know that potential is 1 over 4 pi E naught Q over R. We know V is therefore proportional to 1 over R. Okay, so that's what that's showing us. So once we've got that, we think, well, this must be something we can deduce from the gradient. Okay, now in this situation, first of all, V is proportional to minus 1 over R because it's a negative gradient. That's the first thing. So that's the first thing we see. Because of the fact that it's negative, we know Q must be negative. And what else we could deduce from that is we could actually calculate. We could calculate the charge, okay, from the gradient. So we could deduce the charge from the gradient as well. Okay. I don't think that point I've made there is particularly relevant. Right. Next up, 2C. Most of you got this one right. It's sorted. Use the data from the graph. And when it says use the data from the graph, it means use the data from the graph. It's funny that. So voltage or potential is 1 over 4 pi E naught Q over R. So we need to find out what is R when we just need to basically just basically find the gradient. So we're going to pick some points on here. Now I picked this point here because it's nice on the axis here. Well, did I pick that point? I said 1 over r equals 8. No, I didn't. I picked this point here. So 1 over r is 8, so r is 0.125, and r is 0.125, 1 over r is 8, and v is minus 2000. So with that, okay, if we can basically make q the subject of this equation, we can say q equals v times r times by 4 pi e naught, shoving these values for r, shoving the value for v naught, and q comes out to 30 nanocoulombs, so it comes out to 27.8 nanocoulombs. Right, I went around the houses on this one. There's probably a much easier way of doing this, but yeah, what did I do? I can't remember what I did here. Charge from r to point where r is 0.5 meters, calculate the work done. So basically r is 0.2 and r is 0.5, so I basically went 1 over 0.2 and 1 over 0.5 gives us 5 and set 2. So those are my 2 points in the graph, 5 there and 2 there. Okay, then I read off the different potentials. So I had 1200, minus 1250 and minus 500. Those were our correlating correlating potentials. And then we knew the charge was 27.8. I don't know if we used 27.8 or 30, but we used the charge from that. Oh, sorry, 60 newtons, 60 nanocoulombs. So we put a 60 nanocoulomb charge in there, and I multiplied it by the potential to get the electric potential energy at one place and then potential energy at another place, and then subtracted the difference and it gave you positive 45. I think it's a much easier way of doing it, basically by just doing the difference in potential. But hey, there you go. It comes out to plus 45. C part 2. C part 3. Calculate the field strength at a point where r is 0.4. So we want to say E equals F over Q. That's all good. And the field strength is of course 1 over 4 pi E naught Q over R squared. So taking our values, okay, taking our values that we calculated from the magnitude of charge up here, 27.8 nanocoulombs, shoving that into that, and then dividing by the radius which they've given us. It's a fairly straightforward. It comes out to 2 sig fig anyway, 1,600 volts per meter. Surprising how many people didn't get this. Lots of beautiful answers, but none of them right really. Charge on a capacitor, basically charge is current times time. So if you have a graph of current and time, the area under the graph is of course the charge, the total charge. So you need the area under the discharge curve. Now this question here, 3 marks, we disregarded it because this said 300 kilo ohms. And up here it said to 150 ohms. So we've taken this off the paper, but I think it's worth just taking a quick look at this. Assuming that was 150 kilo ohms and that was 300 kilo ohms, all we've done in this, if this was 150 kilo ohms, we just doubled the resistance, then the initial current, okay, here would be half. So we can just put a point there. That's straight off. That's all we know straight off. Then I'd say, well, look. Here, what is the time constant? We don't know what the time constant is, but if you just go down here and look down here, roughly at 3 intervals of time, if you go up from this line, if you go up there and across to here, this point here is roughly 0.37%, or sorry, 0.37 times the initial current. Okay, so that's roughly that magic value, 0.37. Now, if you think about that, that's of course the time. That is the 0.37 has a significance because the time constant is the time it takes for the quantity to drop to the initial times by 0.37. So here, the initial time constant is 3 units of time. We don't know what they are, seconds, let's just say. And of course, if we've doubled the resistance, then we should double the time constant. So all I've done is I've gone, well, there's my first point, and it's going to take 6 seconds to get to a third of this amount, or 0.37. Sorry, 0.37% of this amount. I keep wanting to say percent for some reason. But anyway, so I'm just sort of going along there and basically saying, well, that's roughly there. So you get this graph doing that. And that's just worth bearing in mind because it's good knowledge to have. All right. So we have for this part B, B parts 1. We've got the capacitance, we've got the potential. If you've got capacitance and potential, you've got energy. Simple as that. Plug in your values, you get 4.86 joules. That's the gravitational potential energy. Boom. Next up, assuming all, sorry, that's not the gravitational potential energy, that's the electric potential energy on the capacitor, the energy stored at the capacitor. Once you've got that, assuming that's converted perfectly into gravitational potential energy, then the height would be that energy divided by the weight, and that gives you 1.39 meters. And then all it says, appropriate number of sig figs, it's all to 2 sig figs, so that would have to be 1.4 meters. Now, once you've done that, why wouldn't it happen in practice? Well, really, it's because the current's going to cause heating the wires. So heating the wires is going to give us some sort of power loss. And friction in the motor, that's going to give us some sort of power loss. I don't know if I should have written more than that, but there's our points, our main points. You could also really say that when the current's too low in the motor, then it doesn't induce any motor effect in the coil, and so the last bit of current won't do anything anyway. It'll just go through the coils. Right. Now, when there's some revision to be done for many people here. The variable resistor set to minimum resistance, so we can discount it. Switch S is shut. As you shut the switch, immediately a current flows around that coil. That coil. As that coil current flows, a magnetic flux is induced in this iron bar, and as the flux is growing in the bar, this is going to induce an EMF in this coil, and that's going to be trying to oppose the flux that's developing. Because the EMF is induced, it's going to induce a current, and therefore we will get a deflection on the ammeter. It doesn't matter which way it goes. Let's say it goes to the right first as we shut it. Soon as the flux is stable, there's no changing flux in there, then the EMF, Lenz's law tells us, or Faraday's law tells us, that the EMF is proportional to the rate of change of flux, d phi by dt. Okay, so if the flux ain't changing, there's no EMF. So as soon as this flux is stabilized, this will drop back to 0, and very few people put that clearly into words. Then afterwards, the resistance variables is suddenly increased, so they crank up the resistance of the variable resistor. Now what that's going to do is reduce the current in this coil. If it's reducing the current in the coil, the flux in this bar is going to try and diminish, and because there's a diminishing flux, we have a changing flux, we therefore have an EMF induced in the second coil. So that EMF will therefore try to oppose the change. So in the first case, it is trying to oppose the flux developing. In the second case, it's going to try and oppose the flux diminishing, and so we'll get a deflection in the opposite direction. Okay, so play that explanation back a million times and make some good notes on that, please. Coil, magnetic field strength, or sorry, flux density, I should say, number of turns, cross-section area, money for jam. This is good. Money for jam. The flux the flux linkage, BAN, as you know, we just plug in our values they've given us up there, real easy. It wants an appropriate unit, so I gave it to the appropriate number of sig figs as well, so we want the answer, and the unit is Weber turns. A lot of people jumped the gun here and went overboard on this. Of course, the coil is rotated through 90 degrees in 0.5, and it's the mean. A lot of people were putting in the sine omega part, which is only the instantaneous, which is only useful for telling us the instantaneous EMF. So basically, just plug in your values for the flux, which you've got from there. That calculation changes the time in 0.5 seconds. 0.12 volts. Okay, there's our heavy mass, 2.25 kgs, moves in a circle of radius 1.5 meters at a speed of 8.6 meters per second. So you can do this various different ways. I just thought this was the easiest way to me. So you can do it with I'll show there's another way, but displacement is velocity times by time. Therefore, if we go, sorry, it's velocity times by time. So if we're going 8.6 meters to 0.4 seconds, it's going to travel a sweep out an arc of 4.44 meters. Now I don't know if that's more or less than one revolution, you don't need to know. The angle therefore would be that distance divided by the circumference of our circle. Okay, so 2 pi times by 1.5 times by 360, that gives us 100. So this is basically the percentage, the fraction of a circle, I suppose. That's what you can do. That's the circumference, that's the distance it's travelled, so this is the fraction of a circle, times by 360 gives you the angle in degrees. Bosh, there you go. 2 sig figs makes it 130. I'm losing my voice. Next up, tension in the string, that's just GCSE, there you go. F equals mv squared over r, plug in your numbers, 12 newtons. Finally, the string will break when it exceeds 60 newtons, so we just reverse engineer this equation. We want to know the number of revolutions, so you can use F equals mr omega squared. You could do that, but it'll just take longer. Omega therefore comes out to the square root of F over mr, so when you put in your numbers for the braking force, we know that omega is 12.6 radians, and once we've got that, well, we can say that frequency is omega over 2 pi, so now we can just find the frequency, and it comes out to 2.01, or again to 2 sig figs, 2 revolutions per second. Now this question here is money for jam. This is the sort of thing, when you see a question like this, you just go ka-ching, thank you very much. They're examining me at A level on GCSE stuff. Please, praise the Lord, this is what you want. But so many people just talk rubbish, basically, and this is what you need to, as a class, you need to all practice the most. Okie dokie. So let's just think about this. They want us to mention all 3 of Newton's laws of motion, so surely going to get 3 marks for mentioning the laws. Then we're going to talk about why it's not horizontal. They're going to give us a mark for picture, and then they're going to give us a mark for some quality of communication. So we know it's going around in a circle. We know there must be a centripetal force providing that circular motion, and that's coming from the tension in the string. Do a little sketch like that. I know it's got an instantaneous velocity that's tangential to the radius of the circle. Finally, if I'm looking at it from the side, let's suppose this is my pivot and it's being swung round and round from the side. Of course, it's got a weight force acting down. Please do not call gravity a force, okay? Weight is a force. It's got the force due to gravity, the weight acting down, and therefore there must be some component of this tension acting upwards. Because of this, therefore we know there'll be some sort of angle. Okay, so I'm going to do diagram 1 and diagram 2 and then go through the bullet points. So the ball is in a circle, not a straight line. So by Newton's first law, N1, some external force must be acting. Piece of cake. Diagram 2 shows that tension is acting at 90 degrees to the instantaneous velocity, so no component of the tension changes the instantaneous velocity, hence a constant speed. Okay, so T, the tension, provides a force, see in diagram 2, so by N2, or by Newton's second law, the acceleration must be present towards the centre of the circle, because an unbalanced force is acting. We call this centripetal acceleration. By Newton's third law, the pivot must provide an equal and opposite force. Okay, there we go. I've mentioned all 3 laws. The ball has mass and hence weight, H is mg. Therefore, to move in a horizontal circle, there must be a force opposing the weight from the string. The string must provide the force to oppose the weight. Hence, the tension in the string must have a vertical component. Well, see diagram 1. I genuinely think, you know, there's about 1,000 things you could write for this, and it's just GCSE. So I really want you to, focus on this. I really want you I don't want you to just copy down what I've written in this, what I've just said in this. I want you to maybe play this video back one more time, and then I want you to stop the video, and I really like you to just see if you can write this down yourself on a piece of paper and look for a minimum of 6 bullet points and then correct it onto this. Okay, that's a little extra homework for you all. Alright, thanks for watching. Sorry that I lost my voice.